Let's take a look at simplifying surds. Now, if you are not exactly sure what I'm talking about, a surd is just an irrational number that involves a root or radical. So things that I'm talking about are things like the square root of 2, square root of 5, cube root of 11, and so on. So we've got the square root signs going on there, or the cube root sign. And they're irrational. They're not like the square root of 9, which you can just reduce to the regular old number 3. Okay. When we're working with surds, we prefer to write them with the number inside. So that's the 2 or the 5 or the 11 or whatever it happens to be. The number under the root sign, we want that to be as small as possible. And we tend to do that. One reason is because it's easier to combine when we're looking at other operations like adding and subtracting surds, and it also helps us with cancelling surds when we're doing multiplying and dividing. So let's take a look at how that works with a couple of examples. So the first one I'm going to do is a pretty fundamental example, I guess. It's not necessarily simple. The idea here is I've got the square root of 384 and I want to simplify that or write it in its simplest form. So looking back up here, I prefer to write my surds with the number inside, 384, as small as possible. And that means extracting out all of the bits which we can actually take the square root of. Because when we've got the square root of a product, that's the same as the product of the square roots. So we can simplify things a little bit. Now the way that we're going to do this is we are going to write the number under the root sign, 384, as a product. And of course it needs to be a product of its factors. So the things that multiply by each other to give us 384. And in particular, we're going to look for perfect square numbers because those are the ones we're going to be able to simplify and pull out. So we're going to look for perfect squares. So it might be useful to have a list of some of the smaller ones. That'll help us. Things like 1, 4, 9, 16, 25, 36, 49, 64 I can fit. Of course the list goes on, 81, 100 and so on. So we're going to look for in the factors of 384 numbers which are perfect squares. So I'm going to start a pretty rough way of doing this. I'm going to say 384, I can see it's even, so it's definitely 2 times something. 2 times 192. So if you're not comfortable doing that, you can plug that into your calculator or do it in long form as well. So 384 is 2 times 192. 192 is still even, so I can pull another 2 out of that. I'll have 2 times 2 is 4, and it'll be 96 that we're left with. Still even, I'm going to get 8 times 48. I'll keep going, that's even too. So I've got 16 times 24. That's nice, that's a square number there. I can keep going again. I might go 4 this time. 4 goes into that, 64. And we're left with 6. All right, I think that's probably as low as I need to go. I know that's even, but I'm not going to get down to the perfect square of 4. I do, however, have that perfect square number there, 64, which is 8 times 8. 8 times 8. So I'm going to go back up to my question here. Square root of 384 is equal to the square root of 64 times 6. Okay, doesn't look any simpler, but I can write that as the square root of 64 times the square root of 6. And then, of course, we can simplify that one. The square root of 64 is just 8. And we're left with the root 6 there. So that's our simplest form for the square root of 384. I don't need to take this one any lower because, as I said before, if we look at the list of perfect squares, 4 doesn't go into 6 evenly, and 1 doesn't make any difference. So we don't even really need to look at 1. So that's our simplest form for that one there. Let's take a look at something slightly more complicated by bringing in some letters, some pronumerals. So let's say I want to simplify 4 multiplied by the square root of 360 x cubed y to the 5th. Okay, so again, we're going to do the same sort of thing. We're looking for the factors of these things under the square root, in particular looking for things that are perfect squares. Okay, So I'm going to go that is equal to, I'll leave the 4 alone, the square root. Now 36 I can see pretty straight away is going to be 36 times 10. 36 is nice because that's a perfect square. 10, thinking about numbers smaller than that, 9 doesn't go into 10, 4 doesn't, so I'll just leave it as a 10. Now here's where it's a bit sort of different. X cubed, we need to think about what's a perfect square that's a factor of x cubed. Well, the only factors of x, while it's still a pronumeral or a variable, are x and x and x. So I'm going to take x squared as a perfectly squared x, and then I've still got the one other x as well. X squared times x is x cubed. And then similarly, y to the 5th, well, I've got y squared, I've also got y to the 4, and times y. Just make sure you bring your square root symbol all the way over to capture everything. All right, let's simplify that down a bit. We're going to have the square root of 36 and the square root of x squared and the square root of y to the 4. You probably don't really need to do this line, but just for here, I'll just show you how I'm getting through the different steps. And then what we've got left over under the square root is the 10, the x, and the y. So 4 times the square root of 36 is 6, so that's going to make 24. The square root of x squared is going to be x. The square root of y to the 4 is going to be y squared. Y squared times y squared is y to the 4. And then left over is the square root of 10xy. Okay, so there we go. A couple of simplified surds. So remember, surds are just irrational numbers involving that root sign or that radical sign. And what we always like to do is write them in a form where the number inside the square root is as small as possible, like we have here. So we didn't need to have y to the 5th because some of those we can take the square root of and bring it out. As you can see, we end up with the y squared. Okay.